Hello, my name is Takazumi, and I am with the Okinawa Institute of Science and Technology. In this presentation, I will be going over our recently published work titled Goal-Directed Planning for Habituated Agents by Active Inference using a Variational Recurrent Neural Network. In this work, we asked, how can agents achieve goals given only partial knowledge of the world? It is believed that agents can never have complete knowledge of their environment because the experience that can be gained in a finite amount of time is limited. However, some agents, such as humans, are able to mentally image plans to do unfamiliar things by generalizing from past experience. In our proposed model, by storing well-habituated sensory-motor trajectories in a low-dimensional latent space, plans to reach unlearned goals can be generated by inferring latent variables following the principle of free energy minimization. In brain modeling studies, it has long been thought that the brain uses an internal generative model to predict sensory outcomes of actions. These three models shown here, implemented using a recurrent neural network and applied to robot control, are tested in this work. One common model is the forward model, which takes the current time steps, motor commands, and latent state to predict the next time steps' sensory values. The stochastic initial state model is based on the frameworks of predictive coding and active inference, and uses stochastic variables to represent the initial state and learn the probabilistic distribution in the trained sensory motor sequences. The proposed model, goal-directed latent variable inference, referred to as Glean, is a further development that enables learning of transitional probability of the latent state at each time step. In this work, we put forward the aforementioned Glean model for goal-directed plan generation. We showed that in a robotic manipulation task, our proposed model outperforms the other previously mentioned internal models. This is implemented using a modified PV-RNN architecture, and this code that we used is now publicly available. A goal-directed plan is a sequence of sensory motor predictions from a known initial condition to a desired goal, given a trained neural network. On the right is a simplified diagram showing a single-layer recurrent neural network in our architecture, unrolled over time. D represents the RNN cells, which takes as input a sample from the posterior distribution ZQ. ZQ itself is a function of the latent variable A, also known as the adaptation variable. ZQ is regulated by the prior distribution ZP, by minimizing KL divergence. Learning is accomplished using the evidence-based lower bound, following the free energy minimization principle. For a more detailed formulation, we refer you to the full text. However, in summary, we consider the prediction error of the generated output and the weighted KL divergence between the prior and posterior mentioned previously. Note that at t equals 1, the prior is a unit Gaussian. The weighting of KL divergence, which we refer to as the meta-prior with the symbol W, regulates how much the posterior follows the observation. It is similar to the beta parameter used in variational autoencoders. Planning uses a slightly different formulation, since we only have the observations at t equals 1 and t equals goal. Prediction error comes only from these 2 points. As planning happens after training, the latent variables are fixed at their trained values except for the A variables that are mapped to sigma and mu of the posterior. The meta-prior in this case controls how much the trained prior influences the inferred posterior. We conducted experiments in 2 settings, one in a simple 2D world and another with a simulation of a robotic arm. The data and the network settings we used are also published with our source code. In order to show the influence of metaprior on learning, we first demonstrate prior generation, which has the neural network generate a sequence with no error signals and a random initial state. We can see that the overall branching structure of the training data has been learned in all three cases. However, with a weak metaprior, the training sequences themselves were not very well learned, leading to large deviations from the expected path, while a strong metaprior caused some of the probabilistic structure inside each branch to be lost. To observe how metaprior affects generation, we now look at posterior generation, where the latent variable a at t equals 1 as learned after training is given. We can see that with weaker metaprior values, the output is driven more by the prior that has learned the probabilistic structure of the data. Although it isn't clear from these figures, there is some skew towards the expected path in the intermediate case, however. With a strong metaprior, the network becomes sensitive to the initial state and as a result behaves more deterministically. In the second experiment, we used a simulated robotic arm doing an object manipulation task. The task was to grasp a particular block and place it on the desired goal. The object and goal positions were randomized around a mean position. To generate the plan, the configuration of the robot and object coordinates at the beginning, along with the final coordinates, are given. Here we can see three networks with different metaprior values controlling the robot arm. The blocks are the objects being manipulated, the disks are the goals, and the crosshairs are the predicted coordinates. With a weak metaprior, while we can see the task is being completed successfully, there is quite a lot of noise in the trajectory, leading to unnecessary movement of the arm. With a strong metaprior, the network ends up ignoring the block position, missing the block, and failing this task. However, with a suitable value for the metaprior, the trajectory is smooth and the goal is completed successfully. Comparing Glean to the two other internal models we mentioned earlier, we can see that Glean performed best in this robotic planning task, with the forward model in particular having a 0% success rate. If we look at an example trajectory, the forward model was unable to generate a long horizon plan because the motor space is large and not very well explored given only the small number of habituated paths in training. It was able to do single-step prediction, however. The stochastic initial state model performed more closely to Glean. However, we can see that the initial state by itself is not always enough to encode the exact transition where the object is picked up and begins to move. In conclusion, our proposed model, goal-directed latent variable inference, is able to perform goal-directed plan generation by generalizing from limited experience and demonstrates better planning performance than other internal generative models. Currently, we are extending this work so planning can happen in real-time, dynamic robot-human collaboration tasks. Thank you very much for your attention.